So I hope you are graduate students, you are PhD or master students. Yes? Are there? Okay, so no undergraduates here? Okay, so good, because it is not very complicated. It is relatively basic, but you need some scientific knowledge in order to understand what I'm talking about. Okay? So what are the objectives of the course? What we want to do is to understand how nanotechnology, which is a big word, a very big topic, very hot topic, relevant to many, many scientific disciplines, from engineering to medicine to materials to environment, how nanotechnology is connected to environmental things. That's the main objective of this course. We will talk about how nanotechnology can help the environment. So we will talk about environmentally friendly and green nanotechnology-based materials and methods. We will also talk about the risks and the damage of nanotechnology to the environment. Because like everything, there is good and there is bad. And nanotechnology can be good, but it can be also bad. And some of the things that we need to do is how to solve the bad things that nanotechnology is doing to the environment. And what else we will do? Just give you some ideas about new possibilities, new research possibilities in nanotechnology. Maybe after this course, you'll go out and you'll do great research on nanotechnology, and you will save the world. Let's hope. Okay, let me tell you a little bit about myself and about my research, because I'm also doing nanotechnology in different aspects. Okay? If you want to learn more about what I do, you're welcome to go to this website. By the way, Professor Patra is here. Nothing more? Yeah. If you want, I can give you all the presentations, and then you can give it to everybody. Okay, so anyway, you can go to this my web page and see everything about me. I work on many, many things, different things. You know, the good things about being a professor is that you can do whatever you want if they give you money for this, okay? So luckily for me, there are many projects that I work on because students came to me and told me they're interesting, and I succeeded in some cases to get money to do the research. So I have a good activity, pretty substantial activity on sensors, specifically sensors for gas materials. And actually, in the middle of the course, I'll tell you about some of our sensors that involve nanotechnology. A very significant part of my research involves very interesting nanomaterials called carbon dots. Carbon dots, we will talk about them a lot in a few lectures. And what we do with them, we make, among other things, sensors. And we also use them for various biological and chemical applications. I also work on batteries and supercapacitors, energy storage. You know, all these things about energy are very important in the world these days. Alternative energy, how to store energy. As you're going to see in this course, nanotechnology has big, big significance for this field. And we also work with nanotechnology in energy storage. And finally, we also work on biological systems. We work on proteins that are very interesting. They are called amyloid proteins. Have you heard of amyloid proteins? They are proteins that make aggregates. Have you heard about Alzheimer's disease? So in Alzheimer's disease, we have amyloids in our brain. We, in my lab, trying to understand what amyloids do. This is not nanotechnology. I will not talk about it in this course. Maybe the next course, maybe the next Gyan course. But this is also something very different. So as you see in my lab, various things from energy to biology, from materials to sensors. So that's what I do, and you're welcome to visit my site, my webpage. And if you have any questions or you have any ideas, please write to me. I'm always happy to explore new ideas and new directions. This is a long list. Professor Patra mentioned this. The course will have 11 lectures, maybe 12, we'll see, because I don't have a feeling how it's going to go. I'm going to talk for 50 minutes, and then I'll leave some time for questions if you have questions. We will also have sessions, some time in between. It's supposed to be for tutorial, but I can answer questions during these tutorials. And also something that I think is going to be very interesting, we would like you to present some research. I understand that you already selected people, so you can select projects or scientific papers and make presentations. I think it's going to be very good for you. So let's just go quickly on the subject that we're going to cover in this course. We will start today with introduction to nanotechnology, just to see why people are so excited about nanotechnology. What is so special about nanotechnology? This is going to be the topic of the first 2 lectures. The second topic will be the bad things about nanotechnology. As we're going to see, nanotechnology or nanomaterials in the environment can be very bad for our health. And we will discuss why. If we understand why they're bad, maybe we can stop them from being bad. And this is actually also what we're going to talk about in this lecture, how nanotechnology can help us overcome the bad things in the environment. The third topic will be green nanomaterials. As you're going to see, nanotechnology and nanomaterials in particular can really help agriculture in many, many aspects, both in controlling agricultural processes and biological processes, and also finding new solutions to agricultural problems, what's called the green revolution of nanotechnology. We're going to see how nanotechnology can help to grow better plants, better crops, how it helps agriculture. The fourth topic will be the relationship between nanotechnology and water. We're going to see that nanotechnology or nanomaterials can be bad in water, but there are many interesting, unique applications of nanotechnology in cleaning water and making water safe for drinking. We're going to describe some of these technologies. Some of them actually we developed in my lab, and I'll tell you about it. The fifth topic, we will go specifically to a subsection of nanotechnology called nanobiotechnology. This is nanotechnology as related to biological systems, and we're going to see how nanobiotechnology is related to the environment, how it's bad for the environment and good for the environment. In the sixth and seventh topic, we will talk about nanotechnology and energy. Because here, in the energy revolution, in solar cells, in batteries, in fuel cells, all this huge world of energy, nanotechnology have really a very important place. And we will discuss it in our topics. The first lecture on this one will be nanomaterials in solar cell technology, mostly. And then we're going to have a lecture about nanotechnology and energy storage. You know, it's not enough to get energy from the sun, for example. You have also to store it for certain applications. This is a huge field in India and in the world, and we will talk about it in this lecture. The eighth topic, we will introduce sensors, environmental sensors. We will see how nanotechnology can help us develop new and innovative sensors for many things, for air pollutions, for water pollutions, for viruses, for particles, for many things. And last, we're going to talk about the future. Is the future good? Is the future bad? There are obviously risks about nanotechnology, like everything in life, but there's also big opportunities. And what I hope that you're going to take from this course is that you, as students, can take the opportunities, grab the opportunities, and make real contributions to the subjects of nanotechnology and the environment. Okay, so that's the first lecture, the first part of the lecture. Let's go on to the second lecture. Or let's start, actually, the course, not the introduction. 1 minute, find it. Okay. The title of this lecture is Nanotechnology from Imagination to Reality. I think it's an excellent title for the subject, because nanotechnology, in large part, started from some dreams, for some crazy imagination of scientists 40 and 50 years ago. These scientists thought that we can do magic things with nanotechnologies, and surprisingly, some of the things really happen, as you're going to see in a minute. So actually, the first discussion, the first thoughts about nanotechnology happened in 1959. This guy, his name is Richard Feynman. Have you heard of him? He won the Nobel Prize twice. in physics. He's really one of the main scientists for quantum physics. And in 1959, he wrote this article that was really not scientific, just like a story. And in this article, he said this sentence, "There is plenty of room at the bottom." And what he meant is that if you go to the bottom of the dimension, to very, very small dimension, you can do incredible things. He didn't know yet, or he didn't say what you can do, but he really thought that in the tiny dimension, the dimensions of atoms and molecules, you can really build a new science. And this was the birth of nanotechnology. Actually, Feynman didn't use the term nanotechnology. This term only happened about 30 years later, as I'm going to show you in a minute. But for now, let's just understand what do we mean by nanotechnology. So nano is actually a measure, a unit. Nano, 1 nanometer is 1 times 10 to the minus 9th meter. 1 billionth of a meter, a very, very small dimension. So nanotechnology is the technology of very, very small dimension. For example, the smallest atom that we know, hydrogen atom, is 0.1 nanometer, 1 angstrom. So nanotechnology does not deal with atoms, it deals with larger entities, even not molecules, some aggregates of molecules. Okay? The human hair, for example, the size or the diameter of human hair is 10,000 nanometer or 10 microns. So the human hair also does not belong to nanotechnology. Nanotechnology is the technology or the science in between the hydrogen atom and the human hair. And if we look at the entire scale of dimensions of the world, okay, and we see that a human, it's a very large human, okay, 2 meter, very tall, 2 times 10 to the 9th nanometer. Okay, and if you go down, if we talk about cells about human cells, about 10 micron. Bacteria, 1 micron, so 1,000 nanometer. And then we go into the chemistry world. This is a colloid of gold, a ball with lots of gold atoms. Here, we start with a nanotechnology world. Gold is about 100 nanometer. Proteins, about 10 nanometer. Small molecules, 1 nanometer, and that's the end of the nanotechnology world. Atoms, very small. They don't belong to nanotechnology. So the term nanotechnology actually was invented in the 70s, okay, by a Japanese scientist. His name was Noro Taniguchi. In 1974, he invented the word nanotechnology. Back then, nobody knew what he was talking about. Technology in such a small dimension. In the 70s, when you talk about technology, you talked about building cars, building giant computers. That was technology. But he had the vision to say that one day we can do technology in the nanoscale. In the 80s, this person, this guy, he was actually not a scientist. His name was Eric Drexler. He wrote a book The name of the book was Molecular Nanotechnology. Back then, when people read the book, they thought he was a joker. They didn't believe. They thought he just went crazy. He had these ideas about making robots that are going to be sizes of molecules. He had talked about nanowires in the size of few nanometers. Nobody took him seriously. But when we look now on the world of nanotechnology, and we're going to see many of the things that he said in his book are actually true. They actually happened. And of course, as time went by from the 80s until now, nanotechnology is everywhere. It's not only in scientific newspapers, it's not only in scientific lectures, but it's also in the newspapers. If you open newspapers, you're going to see nanotechnology in many, many references, in many articles for the general population. I think many people in the streets, even not students like you or scientists, they heard the term nanotechnology. Maybe they don't know exactly what it is, but they heard about it. So you can see these, just a sample of 3 totally random articles from newspapers about nanotechnology. Okay, so nanotechnology in crime, nanotechnology in electronics, and in other aspects. The truth of the matter is that nanotechnology is not something new. This thing, this cup, it's a very famous cup, is in one of the museums in Europe. It was found in a dig. It's an ancient Greek cup. And what the Greek did, even without knowing, they made this cup with the glass, and in the glass, through metallurgy, metal processing, they had some material that when they shine light from the inside, it changed color from white, yellow to red. And you know why? The reason why it changed color, it's called a Lycurgus cup, I think. The reason why it changed color from by light is because inside the glass, they had small nanoparticles, inorganic nanoparticles. And nanoparticles, when you shine light, certain nanoparticles, they can take the light and emit light in a different wavelength. It's called fluorescence. So they saw the phenomena. They did not know why. Today, we know that this is a nanomaterial inside this cup. So we have nanomaterial even 2,000 years ago. Now, why people are so interested in nanotechnology? Why they're so excited about nanotechnology? The interesting, the interesting thing, thank you. The interesting thing is that when you study nanotechnology, you find that there are new physical properties. Okay? And there's new physical phenomena when you go to the nanoscale. There's new materials that you can make using nanotechnology. There is new applications, practical applications in physics, in chemistry, in biology, in engineering. And also, when you apply nanotechnology, you can integrate between different technologies. This is the nice thing about nanotechnology, and this is why many scientists are jumping in the field and trying to do nanotechnology. For example, if we look at these materials here, okay, think about it. We have a copper coin. We have sugar. We have alcohol. We have oil and water. All these materials, they have special properties. For example, copper. What do we know about the coin of copper? What do we know about it? It's conductive. It conducts electricity. It conducts heat. But these properties are related to the fact that we have millions of atoms together. However, when you take copper in few atoms and you make nanoparticles of copper, the properties of the nanoparticles will be totally different than copper, than the copper coin. Sugar. Why sugar is sweet? Because we have millions of molecules in our mouth, going on our tongue, and then we feel sweetness. But if we take one molecule or two molecules, we will not feel sweetness. And if we take few molecules of sugar and we make some nanoparticle of sugar, it will not be sweet. It might be something totally different. This is the secret of nanotechnology. We take materials that you know about, and they give you very different properties. So nanotechnology is also multidisciplinary. You can have chemists doing nanotechnology. You can have electrical engineers doing nanotechnology. You can have biologists doing nanotechnology. Everybody is doing nanotechnology. It's very multidisciplinary. Okay, so now that we know the basics of nanotechnology, why we're interested about it, let's talk about the early dreams of nanotechnology. Ideas and dreams. Some of these dreams came true and some not. All what you're going to see now, these are computer-generated images. Surprisingly, some of these things were made recently and are real. But for now, or 20 years ago, or 30 years ago, they were just dreams. For example, okay, one of the early dreams, actually from the book of Eric Drexler that I showed you before, is to make a gear, just like an engine of a car. But this gear is built from atoms. Each of these are atoms. So this entire gear, maybe 10 nanometer, maybe less. Remember, this is just a picture on the screen, not real yet. Pump. Can we make a pump from atoms? Can we build a nanoscale pump or a nano pump? This is actually something that people succeeded to do. Wheels and gears. Let's see if it's going to work for me here. Yes. Okay. Again, this is a computer movie, but maybe it can be made true. A motor, okay? This is actually like a lawnmower, something that moves, a motor from molecule. And actually, if you see this thing, this is a tiny, tiny robot that actually moves. It's not a nano motor like this, But still, this is something that on the way in 2000 to be a nano motor. Nanowires. Actually, nanowires are some of the best inventions of nanotechnology. These pictures are actually real nanowires that were made in the lab. Now, these days, many people make nanowires for various applications. We're going to see them very soon. Nanotechnology has been applied in great extent to the biological and medical world. I mentioned nanobiotechnology, and now I'm going to show you some examples of nanobiotechnology, both dreams and real things. For example, this is an early picture. What you see here is red blood cells, and here you have a sort of a nanorobot, okay, that goes into your blood, picks maybe a cancer cell, maybe a bad blood cell, and takes it out of circulation. Remember, a dream, but maybe it can be realized. This is another dream. This is a neuron in our brain. What if we can create a little computer, laptop, iPad, that you can put on a neuron and trigger one neuron, or read what the electrical signal in one neuron. This is another dream, how we can take drugs and target them exactly to a specific location of a disease. Okay, 1 minute. Let's see if this movie will work. No, it's not working. Okay. Nanotechnology now. So we saw some dreams, some visions, some ideas. Let's see what actually happened. And the things that I'm going to show you now are development from the past 20 or so years. The first thing is, if you want to do something in science, you have to know what you're doing. It's not enough to stand here and talk about things, show you beautiful pictures and say, I can do this, I can do that. But you have to prove. You have to be able to study what you're talking about. And what I'm going to show you now is maybe the most important tool of nanotechnology, which helps you to actually visualize nanomaterials. And this is called atomic force microscopy. What we see here is an optical microscope. You know why optical microscope is not good for nanotechnology? Anybody has an idea? Why you cannot look with an optical microscope, with a light microscope, on tiny, tiny nanomaterials? Any ideas? The answer is low resolution. You know, with optical microscope, you can see things, the smallest thing that you can see are maybe 10 microns, 10,000 nanometer. This is because of the light that goes to the microscope cannot resolve small nanoscale materials. So optical microscope is not good for us. What is good for us is an instrument called atomic force microscope. Do you know what it is here? you're probably too young to use it. This used to be an instrument for listening to music. Gramophone, sort of. Phonograph, gramophone. You know how it works? This was the record, and the record has heels going up and down, and here you had a needle. And the needle was going up and down, and each up and down gave you a different sound. That's how you could listen to music. Some people say that the music from this phonograph was better quality than what you have today on your cell phones. But I'm not sure. This is like an urban legend. But anyway, this was the way, many years ago, people listened to music. But the concept that we see here, this is exactly the concept of atomic force microscopy. Because what we have in atomic force microscopy is a very, very small needle that the tip of the needle is the size of single atoms. Now, when the needle goes on a surface, it goes up and down, and can tell you about atoms sitting on the surface. So it can help you see nanostructures. So let me show you some examples. Here, what we see are atoms sitting on a surface. These are real atoms. You can visualize atoms. What you do here, we can actually write with the atomic force microscope. This is the needle of the atomic force microscope. You can actually take atoms and move them from place to place. And you can actually write things. Here, this is called AFM nanolithography. With the AFM, with this needle, you can actually write stories. You can write the entire Bible on a tiny rice grain. Thank you. You can actually use the AFM to build new computers, because the tip of the AFM can give you the 0 and the 1, the binary system, which is the basic of all computers. And of course, you can do AFM, as we saw, for nanolithography. Okay, just writing books, writing whatever you want, making any picture you want in a nanoscale using AFM. So the reason I showed you AFM is just because it's an example of a very important technique that can help us understand what we do. If we don't have a way to understand what we do, we cannot make progress in the field and design new materials. This is only one technique, the AFM, one of the early techniques, but it's only one. There's other techniques that we can do, and we're going to just describe some of them right now. One of them is nanolithography. There is this lithography that you can print newspapers or books in large scale. Nanolithography can do the same thing in a nanoscale. Okay? For example, that's what you can do with nanolithography. You can use nanolithography to make small objects that you can then take and use in various devices. From the early days of nanotechnologies, the nice thing that people did is design and produce nanoparticles in different shapes and morphologies. This is here a summary of the various nanostructures that we can make in the lab. And why it is important that we have so many nanostructures. For example, we can have little spheres, we can have nanodiamonds, we can have nanotubes, we can have nanowires, etc., etc. Each of these nanostructures have different properties. Each of these nanostructures can be used for different applications. The fact that we can have so many different nanostructures is the reason why we can do so many diverse things with nanotechnology. Let me just show you some examples of nanostructures that we can use. For example, these are nanowires made from a protein. This protein is called kinesin. It's a protein that you can find in our cells, in our tissues, and we can make nanowires from kinesin. What we can do with these nanowires, I don't know. When people reported these nanowires, they also didn't know. But they said, hey, we can make nanowires from biological molecules, from proteins. As I'm going to show you in a minute, these nanowires can be actually used in electronics. You can take these nanowires and make them conductive, and then you can build electrical circuits using biological molecules. Drug delivery. Drug delivery these days use a lot of nanomaterials. For example, these nano capsules. Why doctors, medical doctors, like nanocapsules? Because you can take the capsules and you can put inside the capsules drugs. In nanomedicine, they are called cargo. So you can take this cargo, this molecular cargo, put it in the nanocapsule, and then you can swallow the nanocapsule and it will deliver the drugs to somewhere in your body. Again, beautiful application of nanotechnology to medicine. Here, I'm going to show you a very interesting nanocapsule built from individual protein molecules. Up. Let me see. I hope. No. Oh, too bad. Maybe I'll show you this after the break. Okay. The world of biosensors and chemical sensors is a very broad world that we have applications of nanotechnology. For example, nanobiosensors. We can take nanocapsules that will contain small molecules that we call them biomarkers. And then using these small molecules, we can sense what's happening in different parts of our body. These are called nanobiosensors. I told you that we can use biological systems in electronics. This is an example of the use of biological molecules in nanoelectronics for sensing applications. What we have here is essentially a transistor. A transistor that goes between one electrode and two electrodes. This is a small wire. On the wire, we put small biological molecule. And when these biological molecules, these receptor molecules, will bind their biological target, the current in this nanowire will change, and we will have a signal. This is called a nanobiosensor. We can have nanobiosensors also in other configurations. For example, we can have an array, a pattern of tiny biosensors. When each of these receptors can recognize a certain molecule. For example, this is a cell that is sick, maybe a cancer cell. If this molecule, this receptor molecule recognizes the cell, we're going to have a signal. Now, this recognition can happen only because this molecule is very, very small. It's a nanobiosensor. Actually, a practical application of this concept of nanobiosensor, is called a DNA chip. This is actually a commercial product that is not so expensive. And what you can do, you can have an array of different receptors, different molecules, and by doing this sensing, you can know if somebody has a disease, maybe has certain cancer or not. There are specific DNA chips for different diseases, all based on this concept. In each well, we're going to have a different receptor recognizing different molecule. I think I will stop now. Okay? Yeah, okay? Do you have questions so far? Don't be shy. Okay? It's totally okay to ask questions. And it's totally okay to tell me, I didn't understand this, I didn't understand that. Okay? Just an introduction. You don't have to ask questions, but just for the next lectures, feel free to ask questions. Questions are the best part of lectures.
If you have question in Hindi, I can translate it in
Ah, okay. I can even learn Hindi. That will be even better.
Sometimes they are not comfortable with English.
Ah, okay. So that's okay. So I'll see you in the next lecture. I put this in here, yeah? Now, yeah, but maybe give them a few minutes to relax. It's very intense to sit for several hours and to listen to science. Don't worry. In my lectures, you'll have breaks between each lecture.
Hello. Good afternoon. I would first like to welcome our guest lecturer, Professor Raj Jelinek. And now it is my great pleasure to introduce Dr. Bishrup Chakraborty from Department of Chemistry, IIT Delhi. He obtained his PhD degree from Indian Institute of IACS, Academy of Cultivation of Science, under supervision of Tapan Kumar Maiti, and later on he pursued postdoctoral research from Ben Gurion University, Israel, and later on the University of Berlin. His research achievements are well recognized. Among many honors, he has been named as emerging investigator by leading scientific journals. And also he has been selected as rising star in organic and inorganic chemistry by American Chemical Society in 2023. And above this, he also served in many editorial boards, including as an associate editor in Frontier in Catalysis. His research contribution is prolific. He has authored more than 80 research publications, 3 Indian patents, and contributed to books and book chapters. So in today's lecture, he will speak us on the topic, electroreduction of nitrate to ammonia on metal oxide nanostructure based electrodes. So please join me welcoming Professor Bishrup Chakraborty.
All right. Okay. Am I audible from the back? All right. Good. So, anyhow, he has given me already my introduction, but I would like to say that I am very happy here that Professor Raj has taken his, valuable time to spend 1 week with you. So I know Professor Raj from my postdoctoral days when I was in Israel. So I know him as a very good professor, a very good researcher, but today I learned that he is also an excellent teacher. Because although during that time I have attended 1 or 2 lectures, not 1 or 2 lectures, 1 complete course in Israel, where Professor Maya Varsadhan has taught us. But I came across from the students that he is an excellent teacher also. So now I got that flavor that he is a very excellent teacher. As he has already introduced, the area of nanoscience and nanotechnology and what are the futures of this nanoscience and what was the past discoveries. He will be definitely sharing some of his research achievements and also other new discoveries that is happening in last few decades. So, well, my journey is now relatively easier because he has introduced what is nanoscience and what we in IIT Delhi we are doing is also very similar in that domain. So, before going into there about what we do or what is our research, I just would like to share you this slide. So, those who have not visited IIT Delhi, so this is our aerial view of our institute, and this is the pointer is not working, but anyhow, this main building. This is our main administrative building, okay, and in the top of almost all the building you can see the solar panels. As Professor Jelinek already told that harvesting solar light is also one of the major domain in nanoscience and nanotechnology. Most of these solar powers or these solar panels are made of silicon wafer or silicon nanoparticle. So anyhow, we are also trying to get sustainable energy from the solar power in IIT Delhi, and also some of you probably know that why Delhi is popular. It's popular for the pollution. All right. So what are the different pollutions in Delhi has? So we have air pollution. What is the major reason? Due to the burning of crops, and it creates also a lot of carbon nanoparticles in the air. That creates a lot of environmental issue. Apart from these small tiny nano carbon particles, we have also plenty of CO2, okay? Because we are burning the crops that is made of cellulose or some kind of carbon. So if you burn cellulose or some kind of carbon fiber in presence of water and oxygen, it will give you CO2 also as the end product. So CO2 is also very challenging, component at this moment in environment that we need to take care of it. Okay. So apart from that, it came plenty of times in the newspaper that we have Delhi city is just on the bank of river Yamuna, right? And particularly in the Yamuna river, those who are following newspaper and concerned about the pollution, they might have seen that sometime on the Yamuna river, in the picture you have seen the foams are coming, right? The white foams on the Yamuna river you have seen might be in the pictures. So what are the cause for that? Anyone has any idea? And there are also rumor in some time you might have seen that some people thought their blessings of some god and people take a dip, they can get cure or something. You might have seen it in the newspaper. These are nothing but these are actually poisons. You know why? Because in Yamuna river, in Haryana, Punjab and a lot of districts in which this Yamuna river is passing, they have a lot of industrial belt. And during this industrial process, plenty of ammonia is being used as a basic ingredient. And during the process, after the process, they releases the ammonia into the Yamuna river because the only way to discard is to just throw it into the river. That is the only way. So that is the reason in Yamuna river, particularly in the winter time, the ammonia percentage reach up to 8 ppm. And if you just think about human concern and environmental sustainability, the ammonia concentration in our drinking water should be 1 to 1.5 ppm. That much we can tolerate. Even less than that, I would say. Even 1.5 ppm is also too dangerous. Now that is the reason we have Delhi Jal Board, which is just beside the Yamuna river. And that Delhi Jal Board is taking care of this ammonia in addition to other nitrogen containing elements or nitrogen containing pollutant that is present in the water, or particularly Yamuna river. Now, this is a very simple chemistry is involved in water treatment. How to get rid of this ammonia. So the simple chemistry is there. If you just oxidize the ammonia into chloramine. So I am sure that most of you are from chemistry background and you know the structure of ammonia or the formula of ammonia. And what is the structure of chloramine? It's nothing but NH2Cl. That means if you replace one of the hydrogen with chloride, then it becomes NH2Cl. Or maybe sometime if you replace two hydrogen with chloride, it can NHCl2. Both are called chloramine. And in terms of activity or in terms of their caution to death, chloramine is much more greener in compared to ammonia. That is why what Delhi Jal Board or what typically once we treat the wastewater, we treat with chlorine gas. So if you treat with ammonia with chlorine, it gives you chloramine, that is NHCl, NH2Cl or NHCl2. Now that is the only way now also how water is getting treated. Now the problem is that once we have 1 or 1.5 ppm ammonia, it can be treated with chlorine. Now once we have 8 ppm, then Delhi Jal Board raised their hand, we can't do anything. Even few days back also we got notice from Delhi Jal Board that we cannot supply water today because we have plenty of ammonia in Yamuna river. So that is a serious concern. Now that is the toxicity I am talking about ammonia. But most of you probably know that ammonia is very, very important because it is commonly used as fertilizer. And whatever the organic compound that are containing NH3, NH2 or any kind of nitrogen functionality, the only source is the nitric acid, right? If you just treat benzene with nitric acid, it gives you nitrobenzene. Now, where from these nitric acids are coming? What is the source of nitric acid? If you oxidize ammonia, you can get nitrate, and if you just protonate it, you will get nitric acid. So, basically ammonia, nitrate, nitrogen, they are in a one cycle, that is called nitrogen cycle. Even in also in biology, in plants, they have also this cycle. Now, why I am emphasizing this point, because this course is particularly for environmental nanotechnology. That means what are the molecules, what are the ingredients, they are good, or certain level if it exceeds, they are bad. Now, this is one part of the story where we need to take care of ammonia. Now, other part of the story is that, as I said, that nitrate is also an essential ingredient, because if you oxidize ammonia, it can give you nitrate, but on the other hand, nitrate or nitric acid is also an essential ingredient for industry. Now, where from these nitrates are coming? Ammonia oxidation. Where from ammonia is coming? Once we are talking about where from ammonia is coming, of course, many of you have read textbook, the classical reactions, that is Haber-Bosch process, right? How many of you have heard about it? Haber-Bosch process? Please raise your hand, don't be shy. Some of you, at least most of you. What is that? Nitrogen to ammonia, right? That is the, even nowadays also industry make ammonia from nitrogen in presence of hydrogen. And do you know what is the temperature and pressure required for ammonia making? Very high. What could be the rough range? 300. 300 is the atmospheric pressure, you need it, and you need 500 to 600 degrees Celsius temperature. And this reaction, it's not so easy. Maybe some of you have visited laboratory, you have seen conical flask, round bottom flask, and did some reflex. But these typical reactions are carried out in presence of some catalyst, and those catalysts are also having a dimension of nanometer range. I will show you in a couple of next slides. In presence of that catalyst, if you heat nitrogen and hydrogen, you can generate ammonia, but the efficiency of this process is also not that much great. It can give you maximum 30 to 40% ammonia, but still this is the only process that industrially ammonia is being produced. Now, today's talk, that's why I particularly chose the electroreduction of nitrate to ammonia on some metal oxide nanostructured based electrodes. Now, then if ammonia can be produced from nitrogen, then why nitrate reduction to ammonia is important? I will come to that point, but before that, let me just show. Oops. It's not working. Oops. Yeah. All right. So before that, I just wanted to say that what else or what in general we are doing there. So one part, of course, so this in this theme, I don't know what happens. In this left hand side, some things are wrong. These are actually the products that we are targeting. So what are the products? Oxygen, hydrogen, carbon monoxide or methane, ammonia, and other part. I'm sorry, there are some I think technical error is there. So that's why these reactant parts are missing. But in our lab, we are targeting mostly the water to split into these two components, oxygen and hydrogen. Now, why water splitting is also important? Because nowadays, hydrogen is being considered as one of the green fuel, right? Why is it so? Because if you burn the normal fuel or carbonaceous fuel or natural fuel, you can end up with a lot of CO and CO2. So, if we can build some engine, and some engines are now available also, there are some Japan, they have already made some engine that can generate hydrogen simultaneously, and using that hydrogen they can run vehicle. So that's why this hydrogen is our next sustainable fuel. All right, and oxygen is actually our side product of water splitting, but it is also environmentally friendly, because oxygen we need it, because it is our only source of, only fuel that we take every day. On the other hand, we have CO2 in our environment, which is coming from environmental pollution or some kind of industrialization, lot of fossil fuel burning. So we have CO2. So CO2 to CO or CH4, if we can make it, so there also we can convert this invaluable or toxic CO2 into CO and CH4. And similarly, as I said, that nitrate can also be converted into ammonia, because sometimes, although nitrates are essential, but high concentration of nitrate is also found in water, and that are toxic for us also. So that is why nitrate to ammonia is also a sustainable conversion, and it can also bypass the Haber-Bosch process that we are going to discuss again. And the fifth one is the conversion of ammonia to NOx or N2. So these are their abbreviations. The first one is the oxygen evolution reaction, that is coming from water splitting, and another component is the hydrogen evolution reaction, that is also part of that reaction. CO2 to CO and CH4, that is abbreviated as CO2RR, that means CO2 reduction reaction. Fourth and fifth are NO3RR, that is from nitrate reduction directly to ammonia. And the fifth one is the oxidation of ammonia to NOx or N2, that is known as ammonia oxidation reaction. So in our lab at IIT Delhi, we are mostly focusing on these 5 different reactions, where in the left hand side, although it is not visible, we have taken small molecules like water, CO2, nitrate and ammonia to convert them into valuable products. So what are the valuable products? Hydrogen is the essential fuel nowadays. CH4 is also required, ammonia and NOx. Now in this conversion, we are normally using a catalyst and light or electricity as a source of energy to convert them. So that's why we have, in our lab, we are mostly converting photoelectrochemical conversion of these small molecules into these valuable products using inorganic nanomaterials as the catalyst. So basically what we are doing, we are developing some nanomaterial as the photocatalyst or as the electrocatalyst to convert them into these invaluable products. Now, what other things we must know once we are doing catalysis? So these things is that, let's say in this schematic diagram in the right hand side, you can see this red tube. Let's say if it is a catalyst. So what is catalyst? Catalyst is I think most of you know, it can be a compound, it can be a nanomaterial, it can be a molecule which accelerate the rate of the reaction from the reactant to product and remain unconverted or unaltered. Okay. But in some recent examples, there are incidents you can find that catalyst either cannot change their structure, or sometime they can change partially their structure or completely their structure. In this case, I can call it's a catalyst, but in the lower two cases, I cannot call it as a catalyst, I can call it as a pre-catalyst. That means if some structures are derived from this thing and this is the actual component of taking part in this catalysis process, then I can call it as the pre-catalyst and partial conversion is happening. So our main target is that we want to develop some earth abundant metal based catalyst or earth abundant element based catalyst to study their activity and also study their stability. Next thing is that whether this catalyst is stable under the catalytic condition or turnover condition, and to understand what is the chemical structure of the catalyst and how its structure is directly can be correlated to the activity of it. The third thing is that how on the surface or how this catalyst is absorbing the reactant, converting step by step. That means whether we can predict the reaction mechanism, because there must be some elementary reactions or multiple steps involved in one of these reactions that are presented in the left hand side. So these are actually our targets. And now, before I move in to the directly to the things, I'd just like to share that these are my students who are actually working, and I'm only presenting and guiding them. So in these first 3 students, they are already graduated. So for today's talk, I'll be mostly talking this third student, Lakshmikanta, who has developed this nitrate reduction to ammonia in electrochemical condition where you can, at room temperature, you can convert or you can prepare ammonia, and how you can bypass the Haber-Bosch process. And now I'll just start from here. Although my animation is not working, otherwise I could have asked you to correlate these 4 pictures on the top. Although the answers are given. So top left is Professor Fritz Haber, second is Professor Karl Bosch, third one is the reactor that has been made by BASF company. It's a German company and one of the ancient company. And in this picture, you might be, if you can see, there is a big steel tube is there. And this is the first high pressure, high temperature reactor has been made in BASF. And in this reactor, they had catalyst which is made of iron. So actually in some of the talks, I used to ask students that can you correlate these 4 pictures. So correlation is that this Professor Fritz Haber is the first person who discovered the ammonia production in the laboratory. Now there is a story behind it. I'd just like to share. The story is, so after the First World War, there was a huge crisis of nitrate, because you know nitrate is the only ingredient that you need to make gunpowder, because in World War, you know, you have to have gunpowder with you, a good stock of gunpowder. Now at that time, the only source of nitrate was South America, somewhere in Chile, and we have in India, we have also plenty of stock in nitrate, but unfortunately, India was under the control of British, so German has clashed with them, so they cannot access the nitrate from India, and also similarly America was against German, so they cannot access the nitrate from there also. So that is why the German government thought, let's synthesize nitrate in laboratory and then it translate in a bigger scale or ton scale in our own country, although we do not have nitrate source. So in this vision, Professor Fritz Haber was working, and he made a remarkable discovery that nitrogen, once react with 3 hydrogen molecule, it can give you ammonia in a certain quantity under a huge pressure of 300 bar and 500 degrees Celsius. And he found it out there is a mixture of catalysts which can be iron, iron oxide, K2O, calcium oxide is required, and it can convert into ammonia. And for this remarkable discovery, he was awarded Nobel Prize in 1918. Later on, because whatever he has made in a laboratory scale. That means 1 ml per hour is was the production rate. But after 1 ml production of ammonia, if you oxidize ammonia to nitrate, it will give you very trace quantity of KNO3 or NaNO3. So it would be no longer useful for making the gunpowder. So that's why Carl Bostek into the action. So he translated this discovery into industrial scale, in a ton scale per hour. So that's why later on he was also awarded Nobel Prize. And now after this discovery, German people successfully develop this ammonia to nitrate, starting from nitrogen as the precursor. So from then onward, this one step or this simplified reaction becomes landmark discovery in the science. And nowadays also in industry, people are doing the same conversion with some modified reactor, not like this ancient reactor that is still in BASF. So here is the history of ammonia production. Now if I just go towards the thermodynamics of this ammonia, then why, I don't know, some of the arrows are not working here, maybe due to some technical issue, but why we need to now at this moment bypass nitrogen reduction to ammonia. First thing is that it's very simple, that if I take a nitrogen molecule, nitrogen is having a triple bond in it. So essentially it is very high dissociation energy is involved. That is around 941 kilojoule per mole if you want to break down nitrogen into ammonia. Similarly, if you notice the previous example, there the catalyst that has been taken is a solid phase catalyst, and now nitrogen and hydrogen, both of them are gaseous phase. So that means we are talking about a heterogeneous phase reaction. Now for the heterogeneous phase reaction, the rate determining or rate limiting steps are basically the adsorption of the gas molecule on the catalyst surface. So here are 3-4 primary limitations once we are talking about Haber-Bosch process, but still I can say there is nothing can beat this NRR or ammonia production by Haber-Bosch. We are just trying in the laboratory scale. Now what is the alternate? In the alternate is that, as we have said, as I have said, that we have plenty of nitrate, and nitrate is also equally abundant on earth crust. So nitrate can be the essential precursor for making ammonia. And if you just look into the simplified reaction, that nitrate reduction requires 8 electron and 9 proton to convert ammonia. On the other hand, nitrogen reduction is technically simple because it has 6 electron, that means 2 electron less. Now if you look into this correlation chart, that means oxidation state versus reduction potential, if you have read the textbook or if you have already graduated MSc, then you must be knowing that redox potential is directly related to some reaction and its chemical equilibria. So if I want to do nitrogen reduction, it needs only 6 electron. If I want to do nitrate reduction, it needs 8 electron. That means electronically, a number of electron requirements in nitrate reduction is higher, but still nitrate reduction is thermodynamically more feasible. Why? Because of this thing, the NO bond dissociation energy is 2-3 times less than the NN dissociation energy. On the other hand also, KNO3 has a high solubility in aqueous medium. So if you want to do the reduction in solution phase, you are good. You can use nitrate and you can do the reduction. And similarly, since nitrogen is chemically inert, it is very difficult to get adsorbed on the catalyst surface. Whereas NO3 minus, in plenty of cases, even molecular complexes, heterogeneous surface, you can see that the nitrate can easily get bound to the surface. That means binding of the nitrate is also favorable. So with this thing, we can say that the NO3RR, which is the short form of nitrate reduction, is thermodynamically slightly more preferable than NRR or nitrogen reduction. All right. Now let's look at how these reactions occur. Oh my God. I don't know. There are some issues. some camera figure was there, that's why it is not appearing. So anyhow, let me just help you to explain. So let's say how the reaction occurs once you do the chemical reaction. So typically if you have a catalyst, so that means a catalyst must be having some surface. Now as I said that once the catalysis occur, the reactant, here we have taken nitrate as the reactant, and nitrate get adsorbed in this side, this. Oh my God. All right, so this dotted line indicate that the nitrate is coming from the top and it is attached to here, and this particular steps we know it as the adsorption of nitrate. Now later on it has been observed that this reaction does not occur in one go, it needs some sequential reactions. So in the first step is the adsorption of the nitrate on the surface. In the second step is the first 2 electron reduction and 2 proton involved there. It gives you nitrite, although the structure is missing here, but please assume that here is a nitrite, that means NO2 minus, which is attached to the catalyst surface. And in the subsequent step, it is involved multiple electron and proton coupled reaction to give you the corresponding ammonia plus water. Now why I have highlighted this particular yellow section? Because these are very, very crucial to control the rate of the reaction on a heterogeneous surface. Now if you look further detail into the process of nitrate to ammonia, we can find it out, as I said here, this adsorption on the catalyst surface. Since we are doing electrochemical reduction, so we need an electrode, and there on the top of the electrode we kept catalyst loaded, and nitrate has to come and bind. I think it's pretty sensitive, the screen is sensitive. Yeah, so nitrate needs to come and bound to the catalyst surface, and then this RDS means is the rate determining step, that how it is bound to the surface and how it is converting to nitrite then, because as I said that these two steps are very, very crucial, that whether the catalyst is very nice, that means it is very fast, it is giving good adsorption or so, and now after that there are multiple possibilities. What are the multiple possibilities? It can take up electron, proton, it can generate to nitrogen. So if I convert nitrate to nitrogen, then our actual process is not succeeded. On the other hand, if you do stepwise electro reduction, then you can end up with nitrate, but there is a chance that you will be losing your sum of the product if you cannot control the pathway towards either this or towards this. That means we have 4 parallel pathway for nitrate reduction. Now if you cannot build a very selective catalyst, that means if a catalyst can selectively perform your nitrate conversion through this pathway or this pathway, then only you can able to make ammonia on electrochemically, through electrochemically on a heterogeneous catalyst surface. Now other difficulties also, because as I said that the reaction although looks very simple, but it did not or it do not occur in a very simplified manner. You have a possibility that you can lose in the middle and it can end up with some other product. Other product is also there, that is the hydrogen. I'm again sorry for this thing because some technical glitch with this computer and my pen drive, that's why some of the things are not appearing properly. But here I have just tried to mention that once we are doing a reduction of nitrate to ammonia in aqueous medium, there is a high possibility that you can end up with reduction of your water to hydrogen. Although hydrogen is good, but in this process we need ammonia as the only product. So that is why nitrogen nitrate to ammonia is although very demanding, but on the other hand it is very challenging to do, because you have a chance that you will not reach to your target product. Okay. Now, regarding the catalyst design. Now, what kind of catalyst would be more beneficial for us? First thing is that catalyst must be very reactive. Okay. Second thing, it must be cheap. That is also one way. So that's why I have given you this schematic diagram, where in this triangle, these three vertices are the efficiency. That is the one parameter of a catalysis. Efficiency means once we are doing electrochemical reduction, that means the operating potential. That means how much in terms of energy, how much less energy you need or how much more energy you need to convert this. And second thing is that kinetics, that means how fast the reaction is occurring or how slow the reaction is occurring. Okay. So these are the two thermodynamic parameters. Now second is the economic part, that means cost part. So if you, let's say if you build up or if you make a catalyst out of platinum or gold, then I must say that you are very rich chemist. So that means you need a earth abundant metal, and catalyst must be made of inexpensive sources or inexpensive elements. Now last part is the sustainability or stability. That means if you have made a catalyst, it just lasts for one day, and after one day your catalyst get degraded, there is of no use in industry. If you go for industry, you need at least 1 year, you have to run the catalyst, and then only you can recycle it. So this is why that performance matrix has to be very strong. That means catalyst has to be recyclable. So that's why if you want to build up a catalyst, you must be maintaining this triangle perfectly aligned to make it a perfect triangle. Now in practice, again there are some missing things here. In practice, it has been observed that the ruthenium, platinum and iridium, these three metal based catalysts are the best electrocatalyst. Why? Because their efficiency is the maximum and stability is the maximum. I intentionally draw this triangle imperfect to show you that the cost of the catalyst is pretty higher. So if cost is very higher, then that means this ruthenium, iridium and platinum, although their performance is very excellent, but they are not sustainable catalyst. Now in this particular chart or this plot, I have just shown you that just to correlate this triangle with this natural abundance of the element, there are certain region. So this green region represent that which elements is highly abundant or the earth crust. Now if you look into this yellow region, that means abundance is pretty lower. In that region these three metal arises. That is why if you, let's say if you go to a laboratory, you will be finding that if you want to purchase platinum salt or ruthenium salt, 1 gram of the salt can cost around 20,000. So you must be thinking, or you must be taking care of the cost of the catalyst. Now the thing is that why noble metal are best, because again the diagram is missing. Let's assume that here you have a nitrate molecule and here you have the metal. Now if you just take NO3 minus and one of the oxygen is coordinating to a metal center, and I have drawn it here the orbital diagram that could have helped you, but unfortunate thing is that it's not working here. If you have a metal rich of electron, then the pi star of the NO has to be coordinated back with its pi electron, so that the bond dissociation energy drops. That means in order to do nitrate reduction, you must be taking a metal catalyst which is having rich of electrons, so that you can reduce the pi dissociation energy, giving back the electron density here. So that is why you need a electron rich metal. That is the bottom line from this slide. Now what we are looking for? So as I said that we are looking for basically earth abundant element based catalyst, and so far we have taken this part of the periodic table where these are the 3D elements we have chosen as the precursor, and these are the 4D and 5D element as we have chosen, and by doing simple permutation combination we can build up this wolframite type bimetallic metal oxide. Okay. As I said, these reactions are pretty simple. If you just take this precursor and put it in a normal reaction condition, you can end up with this wolframite structure, and this indicate the one of the unit cell of the catalyst, and this color code indicates that it has two metal center in it, and that's why I have given that these are bimetallic oxide. And the advantage of these two metals are that you have redox active metals, which are these 3D elements, and molybdenum and tungsten are also redox active, but here they are having plenty of electron density present in them. Now on the other hand, if you just do or if you change the reaction condition, you can end up with some molecular clusters. These are not nano structure, these are relatively less in size, less than 1 nanometer their structure. So their molecular cluster also you can prepare out of these 4D and 5D elements. So they are commonly known as polyoxometallate because the multiple metal oxo centers are connected with each other through oxo bridging link. So these also we prepare in our lab, and also we made some metal sulfide. That means if you take a metal salt and if you take any kind of chalcogenides, let's say sodium sulfide, and if you just do some reaction, you can end up with metal chalcogenides inorganic compound. So these 4 or 5 different material we are preparing in the lab, or we have prepared in our lab, and once we have characterized them, we find it out that their morphology and structures and other thing actually fit into the nano domain. So that is our actually primary target of this course. So that's why I prefer to take you here that this two kind of structure for today's talk I will be talking. One is the LDH, that means layered double hydroxide, and another is the polyoxometallate stabilized metal oxide core, because both of them are having a dimension of nano regime. All right, and we are particularly focusing on this nitrate to ammonia conversion. Oh my God, again some of the figures are missing, but these two pictures were taken at BGU. These are my during my postdoctoral study. Here I am trying to give you a flavor, a simple experiment. Let's say if you went to a lab and if you have taken ferrous sulfate in an aqueous medium, so what will happen? It will give you a colorless solution. And why it is colorless, or why there is no precipitate in it? Because the iron salt is very, very soluble in water. Now if you just check the pH of this solution, you will be seeing that pH is around 2 to 3. Okay, there is nothing bad in it, because all the ferrous or ferric salt, they are aqua acid, so they will give you the pH relatively 2 to 3. Now the point is there, if you just start adding sodium hydroxide or any kind of base in it, you will be start making insoluble ferric hydroxide. As you can see here, this is the logo of this BGU is visible, whereas once you have added NaOH and if you made the pH 7, everything is getting orange cloudy solution. Now what chemistry is behind it, or what is happening here? Now what is happening, although the scheme is missing, once you have taken a ferrous salt, that means in aqueous medium, iron is surrounded by with 6 water molecule. There is a simple coordination chemistry in it. Now, once we are raising the pH towards 7, you are adding hydroxide into it. And why then color is orange? Because in water we have plenty of dissolved oxygen, and water medium, it gives you oxidation of iron 2 to iron 3, and all the way around you have a lot of hydroxide in it. Now, it gives you coordinate replacement of water with hydroxide, and as we know that hydroxide is a good bridging ligand. So, it started bridging with next iron atoms. Now, slowly, if you cannot control this bridging process, it will end up with all of a sudden a precipitate that is commonly known as amorphization or amorphous precipitate. Okay. And similarly, if you just look into the aqueous speciation chemistry, you can find it out that in pH 6 to 7, iron is mostly insoluble in nature, right? And now, the point is here, although it is not part of nanotechnology, in our blood we have plenty of iron, and our blood pH is around 6.8 to 7.2. Now, then what is the reason that iron is not getting precipitated out? What is there to protect us? To protect us, we have protein, all right, and proteins are made of amino acid. These are amino acid polymers, and they are protecting the iron. And there is one specific protein which is very important for us, that is called ferritin. I don't know how many of you heard about its name. Now, why I am taking this name of this protein? Because the ferritin is a hollow protein, and if you look into its structure, or if you just check the textbook, you will be finding that it has a hollow cell. Inside the hollow cell, you have iron atom preserved in +3 oxidation state. Other than this protein, iron is present in +2 state in almost all metalloprotein. So, except this protein, you will be finding iron 2, because iron 3 is toxic for cell. Now, important thing here is that in this protein, inside the structure or inside the protein, you can store 3000 to 4500 iron atoms at a time. And another interesting fact is that many of you have seen rust, right? If you keep an iron bar in water and oxygen, it gets corroded immediately and it give you rust. So, what is the structure of rust? It actually having a very similar structure what is present in the core of the ferritin. Now, if you measure the ferritin structure, you will be finding the ferritin is having a dimension of 1.2 to 1.5 nanometer. So, which is slightly relatively less in size, but it is also close to the nanostructural regime, and the core structure of ferritin is having a similarity with the rust structure, and that is the structure of actually the insoluble form of the rock, which are basically iron oxide. So, one of the structure like this one is having a structural similarity with ferritin, and also this during this experiment what you are making, this FeOH whole thrice, if you just slightly warm this mixture, you will be ending up with beautiful crystalline material with nice edge sharing structure, and if you control their structure with some surfactant or with some ligand, you can make nice nanostructure of iron oxide or iron oxyhydroxide. And these particular 4 polymorph means they have a similar composition but different packing in the 3D packing. So, that is why you can see they have a different packing, and this is the iron oxyhydroxide. Why these are important? Because these 4 structure or iron oxyhydroxide are very, very reactive in compared to the stable form of iron oxide minerals like hematite or magnetite. Now, what I am just showing this slide because in our lab we are trying to synthesize some of this insoluble iron oxyhydroxide nanostructure core completely dispersed in water in presence of some inorganic or organic ligand. And another thing is that in the second slide I have shown you that this iron is the only metal which has been used to convert nitrogen into ammonia in the Haber-Bosch process. So that is the reason we have chosen that iron as the one of the metal for converting this. Now let's look into some literature study, because once we are starting some research you must be looking into what is there in the literature. So here, as I have already shown, that there are plenty of possibilities of having nitrate to ammonia conversion. Some of the literatures are known that this delta form, there are 4 different polymorphs are there. The delta form is one of the active form of iron oxyhydroxide, and it can nicely bind this nitrate on the surface, but nothing till now known that how this delta form of FeOH convert ammonia from nitrate reduction, okay, because it is quite unknown that how it is getting converted on the surface of delta FeOH. So that's actually triggers our mind that let's look into this particular material, and let's look deeper that how we can predict the reaction scheme on the surface. And that's why we took some different form of iron oxyhydroxide, and already in the last 2 years back we have seen that if you make the crystalline form of gamma FeOH, polycrystalline form of gamma FeOH of 2 different category, alpha and gamma, there is a competition, and in this competition we can see that the amorphous form or the polymorph of the gamma form, polycrystalline form, it actually gives you better result once you put on the surface of that. So that actually helps us to choose this gamma FeOH as the one of the important material for us. And we again, okay, something is missing, but this is nothing but a ferrous salt. So that's why we took ferrous salt as the precursor, and we tried to prepare different form of iron oxide. So what are the different form? One is the polycrystalline form that we have made. Just simply if you take ferrous salt in ferrous sulfate form, 24 hours room temperature if you prepare, some cloudy orange precipitate will come out. If you just put it under the microscope, you will be finding they do not have a definite surface boundary, and they are commonly called as amorphous, or sometime if they have some partial crystallinity, that can called as a polycrystalline gamma FeOH. Now if you heat them slightly higher than room temperature, that means 75 degrees Celsius, you can see there is no other surfactant or any other molecules are present, and you can build up very nice nanoplates. Nanoplates where? Why? Because you can see there are, sorry, it's very sensitive. These are having a dimension of little more than 100 nanometer, these individual plates. And on the other end, if you just heat them slightly higher temperature like 190 degrees Celsius, the phase completely changed to alpha Fe2O3, that is actually the hematite, and the shape of this material is also like a flex kind of structure with having a dimension of 100 nanometers. So in this we can make some nanoparticles of iron oxide in 3 different form. So one is nanoplate kind of morphology, another is nanoplate, and the first one is the polycrystalline gamma FeOH. So these two are nanostructure, and these two is a amorphous material. Now these are the image that we got from some microscope. So Professor Raj already told you that for the nanoparticles we cannot use optical microscope. So these are taken under electron microscope, just by doing some normal electron microscope. And another study we have done, so these are their individual particles. Now once we are doing electrochemistry or catalysis, you must be looking at the surface. So that's why we took a contact angle measurement. So I'll tell you what is contact angle measurement. We take the bulk material, we paste them as a film, and we drop casted water in it. Now this is a basic surface tension and viscosity, you have read it in your masters, that a surface, if it is having a higher energy, it will, and if it is hydrophilic in nature, it will absorb water or aqueous medium very fast. That means you can, if the surface is hydrophilic, you will be getting a acute angle, right? So 24 degree is the acute angle that we got for this gamma FUH crystalline, that is this one. Other angles I am not showing, but they appeared as almost hydrophilic in nature, but there is a slight difference in their contact angle. That means that all these three material, their surface energy is close comparable. So that we can conclude from this study. Now the next study what we did, next study is this adsorption, gas adsorption desorption. Once again I have said these are all surface measurement or surface characteristic. So in this gas adsorption desorption, this isotherm, these are known as isotherm, there are some technique in which you take your powder sample and fill it with gas at low temperature. How much is the volume change? That gives you the idea about the surface. So from there we can identify that this gamma FUHC, that means this one, the crystalline nanoplates, are giving a relatively higher surface. So as we know that higher surface means higher probability of adsorption of your analyte. So from this study we can conclude then that this material is having a higher surface and also higher surface energy. Next thing is also another technical term, that is double layer capacitance, that is coming from electrochemistry. So I will not tell the details because it will take some time. The observation is here again is very similar. Now once we have these three nanostructure material, you can find it out. The slope is steep for gamma FUHC, that means the crystalline form of gamma FUH is having, again electrochemically once we have determined the surface area, that is also higher. Alright, now oh my god, anyhow I don't know how to present this because everything is lost here. Do you have a spare laptop? Maybe I can connect it. Although my time is very short. But anyhow, let's, I don't know, because these are some important files that I wanted to show. Can you quickly connect it? I think I'll just from here. इसको ओपन कर दो. Yeah, all right, it's coming like this. All right. Sorry for this interruption. All right. So I went again from here. So here from this slide we can conclude that this particular gamma FUH is, as we have proved, that it has a high surface energy. Now since our main intention is to do the electrochemical reduction of nitrate to ammonia, so what we did, we just have taken all these three material and put it on the electrode surface one by one, and we polarize the electrode towards negative direction. Now what does it mean? It means that now electron is flowing from this electrode to catalyst, and whatever the analyte is getting adsorbed on its surface, it is giving the electron. So that's why in this particular plot what we have done, that we have varied the potential of the electrode from positive to negative. That is the bottom line here. And we have just recorded that how much current or how fast current it is flowing through it. And this is typically known as the linear sweep voltammetry. So where we are changing the potential of one electrode towards one particular direction. And here, since we have moved from positive to negative, that we commonly call as cathodic direction or cathodic process. So in this cathodic process, what is happening? The electron is flowing through electrode to catalyst to the analyte, so that we can reduce the nitrate to ammonia. Now how to interpret this data? Interpretation is very simple. Just from a basic sense I can say that whenever we can reach most negative electron or most negative current density, that gives you better activity. That's how a layman can interpret. So from this, in a particular buffer pH 7, because the nitrate is mostly soluble there, you can take the competitive or comparison as the mark to check the activity. So here you can see that the gamma FUH, once you have the nitrate in the electrolyte, you are getting highest current, and this dotted line is representing that once you do not have any nitrate in it. So that means once you have nitrate in the electrolyte and catalyst is gamma FUH, you are getting highest catalytic current. That means there are catalytic conversion of nitrate to ammonia. Now just to prove further that nitrate reduction or this current is due to the nitrate present in the electrolyte, you can vary the concentration of nitrate, and you can correlate that with the variation of the concentration your activity is increasing. And here is the linear correlation, just log J log nitrate. There are some little bit of mathematics, and from there you can get the expression that how nitrate is participating in the rate of the reaction, and from this we can say that nitrate, the order of the reaction with nitrate is 1. So these are simple electrochemical experiment. Another experiment we did, instead of having a static electrode, we just rotated the electrode because of there are some inner process, some diffusion control process, just we want to avoid that part. And we have seen that the rate of the rotation of the electrode is directly related also to the reaction, and from there we can also analyze, just forget about the equations or something, just take the chemistry behind it, that from there we can again get the idea that how many electrons are actually involved in the rate determining or rate limiting step. So this experiment is saying that in this process, once the catalyst is gamma FUH, your rate limiting step is the first 2 electron reduction. So that means once you are converting nitrate to ammonia, the nitrite is forming as the rate limiting species, and it is actually controlling the overall reactions. So that's what we understood from here. Now once we have, as I said, that I have taken 3 different material with 3 different morphology and 3 different surface energy. So we must compare their activity in terms of Faradaic efficiency. That is one term by which we determine for a simple chemical reaction, how do we know that the chemical reaction is very efficient? That is the yield. And in electrochemical process, we represent it as the Faradaic yield or Faradaic efficiency. That means how many electrons you are giving and how many electrons actually you are giving, it's participating in the reaction, and that fraction is represented as the Faraday field. So maximum Faraday field means maximum efficiency of the catalyst. So here from this bar diagram, this red y-axis is the Faraday efficiency, and you can see here that gamma FUHC, that is the crystalline form of this gamma FUH with this layered structure, is giving the best yield. On the other hand, this sub y-axis is the yield rate, that means how much amount of ammonia is being produced per hour. So it gives you a amount that is almost 18 mg, 18 milligram per hour per centimeter square, because we have taken a 1 centimeter square surface area of the electrode. So these matrices we have got, and from there we can conclude that this is the best active catalyst. We have screened other possible options also, varying the pH, varying the concentration, and we got that this is the 84% is the highest possible ammonia we can produce with 18 mg per hour is the rate. And also, once you are doing this kind of thing, you must prove that your ammonia that is you are getting in the process is actually coming from nitrate, because you have nitrogen in the environment that can be also present in your electrolyte. So that's why what we did, we just replaced normal nitrate with level nitrate. Level nitrate means we have taken 15 isotope containing potassium nitrate as the electrolyte, and we did proton NMR. Okay, some of you, if you are PhD student, then you must be encountering this kind of proton NMR, I assume. So once you have 14 nitrogen in your ammonia, it gives you splitting of these 3 peaks. That is because of 14 isotope. Once